So I start with H is of class C1 in RD, is non-negative, is strictly convex, and the limit when s goes to infinity of h of x over x to the power p equal to infinity for some p which is between 1 and infinity. And we saw that this condition, and it is part of the homework, number 3. This condition is is enough to imply that gradient h from RD to RD is a homeomorphism. And you have a representation formula for each inverse. The inverse is the gradient of the Legendre transform, where h star of z is the supremum over x in RD, x z minus h of x. And again, what this condition is here for is this term grows linearly in x. This term grows superlinearly in x. Therefore, this term dominates that term. And if you take a maximizing sequence, it has to be bounded. Otherwise, this will go to negative infinity. The fact that it is bounded implies existence of, first, existence of a minimizer, and second, it implies that h star is always finite. Now, strict convexity is equivalent to differentiability of h star. So h star is a strictly a convex function is strictly convex if and only if the Legendre transform is of class C1 on its domain of definition. But here, the domain of the definition of Legendre transform being RD, it implies that h star is of class C1 everywhere. And just for convenience, I have assumed that h of z is h of x is h of negative s, so that if c of x, y is said to be h of x minus y, c of x, y will be equal to c of y, x. This is just for convenience because otherwise I'll have to define the upper C transform and the lower C transform. And when H is symmetric, I don't have to give you both definition. I just give you the definition of a C transform. So another thing we assume that rho naught, rho 1, are from RD to 0 infinity are probability density, which means that the integral is 1. The support of rho naught and the support of rho 1 is contained in a ball of center 0 radius r. So I have defined mu naught to be rho naught dx and mu 1 to be rho 1 dy. So we have been interested in the following function, j of uv equal to the integral over rd of u d mu plus the integral over rd of v d mu 1, where uv belongs to C. And this means that u of x plus v of y is less than c x y for every x y in Rd. U v from Rd to negative infinity plus infinity are upper semi-continuous. And I want to exclude the trivial situation. U is not identically negative infinity. V is not neither equal to negative infinity. So let me recall one last thing. Gamma is in gamma mu naught mu 1 means the first projection, P1. The first projection of gamma is mu naught. The second projection of gamma is mu 1. And this means, by definition, P, by definition, T, push forward, call it L pi, push forward gamma of A equal to gamma of P inverse of A. Okay. This is what a push forward means. And so this one is equivalent to mu naught of A is gamma of A cross Rd, because P1 of xy is x, P2 of xy is y, and so mu1 of B is gamma of Rd cross B. So one of the things we proved last time is halfway to our duality. J of uv is smaller than or equal to, say, the cos associated to gamma, which is by definition the integral over Rd cross Rd c xy gamma dx dy if uv is in uc and gamma has mu naught and mu1 at its marginals. So the fundamental result we are after is to prove that V sub equal to data F. Okay, so let me repeat again. What happens often in the calculus of variation, you have a minimization problem, and you have no idea how to prove that a minimum exists. Then you invent a maximization problem. So I want to minimize a functional. I don't know if the functional admits a minimum. So I am going to invent another functional, which is such that the graph of the functional invented is below the graph of the function I want to minimize. Okay. So if I can find U naught, V naught, if I can find U naught, V naught, and gamma naught, such that the graph of the white function and the graph of the purple function, they intersect at U naught, V naught, gamma naught, it means that gamma naught minimizes the white function and U naught, V naught maximizes the pink function. And so the natural question is, how do you invent such a function, this new function? It is based on a minimass principle, which I am not going to comment on here. But I gave a detailed explanation in my notes, lecture notes, at Carnegie Mellon. University. And this is on my website. So there I gave a formal argument how to guess the functional J, and what are the indications that maximizing J will be the dual of minimizing the cost function gamma. So here, this is the situation in which we are. We have seen that it was easy to prove this inequality. And let me recall it very quickly. And now I will be formal because we have a rigorous proof last time. U of x plus V of y is less than C sy. If this is true, I integrate over gamma. Now I break the integral into two integrals. This is the integral of U of x, gamma dx, dy, plus the integral of V of y, gamma. Now, this condition, if you replace u by a characteristic function, this condition is telling me that this is the integral of u d mu naught. And that condition is telling me this is the integral of v d mu 1. And so we have the required inequality. Here is what I want to do next. We are in this situation. I am going to look at a subset of a set of gamma. I am going to look at a subset of a set of gamma. If I can show that the purple function coincides with the red function, then this is even stronger than the duality result I am looking for. The red function is going to represent a Monge problem. The white function is going to represent a Kantorovich problem. And so what I'm going to prove is minimizing the function of Monge is equivalent to maximizing J. And as a consequence, we will get that minimizing Cantor-Rovich functional is equivalent to maximizing J. So now let me write my strategy. What I just said, let me put it in words. I start with the following remark. Let T, let tau, mu naught, mu 1, be the set of T from Rd to Rd, Borel, such that T push forward mu naught to mu 1. The Monge problem consists in minimizing a cost function over that set. I claim that we have that this set is a subset of the set of gamma which has mu naught and mu 1 as its marginals. And I will show that when you extend a Monge function to that set, you get Cantor-Rovich function. So in other words, I started with my minimization problem. I want to minimize this white functional. Now I take a subset of the domain of definition. And so clearly, minimizing on the red subset, we get a value which is bigger than or equal to minimizing on the white subset. And so the first plan is to prove that both minimum are the same, both infimum are the same. So let me prove this remark. Proof. Let T be in tau mu naught mu 1. Meaning T is going to push mu naught to mu 1. Set gamma T to be the identity cross T, push forward mu naught. So the identity cross gamma T, the identity cross T, this is a map from Rd to Rd. This is a map from Rd to Rd. The product is a map from Rd cross Rd to Rd. And so I am pushing a measure on Rd into Rd cross Rd. Let me check that this gamma has mu naught and mu 1 as marginals. Gamma T of A cross Rd, I want to know if it is mu naught of A. And then I will do the same thing, gamma T of Rd cross B. I want to see if it is mu 1 of B. So let me use the definition of push forward. This is mu naught of a set of X such that S, T of X, belong to A cross Rd. That is the definition of push forward. But this condition, T of S belong to Rd, is not a constraint because we know that T of S belong to Rd. So this is the set, the measure of the set of X such that S belongs to A. And that is mu naught of A. So we have achieved the first goal. Similarly, you repeat the same argument. Gamma T of Rd cross B is mu1 of B. And so this concludes the proof of the remark. An equivalent way of writing this identity is it means the integral over RD cross RD of f d gamma t is the integral over RD of f of x mu naught dx. Right? So if you take f of x to be the characteristic function of A at x, you see that this identity is exactly that one. Okay. And as I said several times, if we know these two integrals are equal for characteristic function, then since every function is a linear combination of characteristic function, we know that it's true for every Borel function, such that provided that one of the left of the right-hand side exists. Now, let me replace f by c. So observe that the integral over RD cross RD of c actually here it is f of xy. It is the integral over RD cross RD of f of xy gamma t dx dy is the integral over RD of f of x t of x mu naught dx. Yes, this is what it is. Okay. So before, a minute ago, I was referring to that. Actually, what I should referring to is the definition of push forward. Now let me replace f by c. I'll have the integral of c of x, y, gamma t, dx, dy, equal to the integral over RD of c of x, t of x, mu naught, dx. Call this the Monge cos. Then I see that the Monge cos equal to the Kantorovich cos. So this set is a subset of that set, but the Monge cos extends to Kantorovich cos. So here is the conclusion. When I minimize over the Monge cos, over Kantorovich cos, gamma, this is less than or equal to minimizing over the set of T, which push mu naught forward to mu1, the cos gamma t. So I am saying minimizing over a larger set, I get a value which is less than or equal to minimizing over a smaller set where the gamma has a spatial structure. But this is minimizing over the set of T, which has mu naught and mu 1 as marginals. And we've seen that the Monge cost applied to gamma T is, the Kantorovich cost applied to gamma T is the Monge cost applied to T. Call this first conclusion. Second conclusion. By I, if we can find T naught, which transport mu naught to mu 1, and U naught, V naught in C, in UC, such that J of U naught, V naught is the Monge cost of T naught, we will have proven that first T naught is less than or equal to T naught is a minimizer for Monge cost for every T which transport mu naught to mu 1. And second, we'll have proven that the infimum over gamma, which has mu naught, mu 1 as marginals of the cost of Monge, is the infimum over tau, mu naught, mu 1 of the Monge cost. And this will be the supremum over UV in UC of J. Okay. So the task I want to complete by the end of the lecture today is to establish this equality. And if we establish that equality, we are done for existence of an optimal map in Monge problem. And we will have also established the one of the fundamental results of the Monge-Kantorovich theory. So what I done last time was we observed that the functional to maximize a linear function. The set on which we are maximizing is a convex set. And so if we will expect a maximum to exist, it will be at an extreme point. So we started with the condition U of x plus V of y is less than C of x for every x and y. And the plan was this inequality given x, it cannot be true that U of s plus V of y is strictly less than C of xy for every y. If that happened, UV cannot be a maximizer. Because if UV was a maximizer and I have straight inequality, I increase U a little bit. And in this expression, if I increase u a little bit, I am going to increase this value, and that will contradict the fact that I have a maximizer. And of course, all this argument I just comment on will be based on the fact that u is continuous. If I don't know that the maximizer is continuous, I will not be able to complete my argument. And based on that, I introduce, so let me recall, reminder. First, if u is from Rd to negative infinity plus infinity, the C concave transform of u is uc y equal to the infimum x in Rd of cxy minus u of x. And we made the observation that if u is identically negative infinity outside the closed ball of center 0 radius r, every time x is outside the ball, this takes the value plus infinity. And so I can rule it out from the theta I am minimizing. And so I can write that uy of y is the infimum x in Rd, s in the ball, cxy minus u of x. And we have concluded that, hence, either uy is identically negative infinity, or the Lipschitz constant of uc, The Lipschitz constant of uc restricted to the ball is less than the supremum of the gradient of h on the ball of radius little r plus capital R. And this is what we establish. Okay. So if it looks like a mystery you don't remember, let me comment quickly how we proved.
So for the existence of this inf, you need to put some condition on u, or you just take values in the interval?
For the existence of?
The infimum.
Yes. Oh, the infimum may be negative infinity.
Right.
Yes. This is why I am saying either UC is identically negative infinity, but if it is finite at one point, then it is finite everywhere, and you have this property. So to prove that, what we did last time, we wanted to compare UC of y2 minus UC of y1, which means here I will replace y by y2 and y1. And we saw that C of x, y1 minus C of x, y2 is h of x minus y1 minus h of x minus y2. We use Taylor, the mean value theorem, to say it is gradient h of sum z, y2 minus y1, because the difference between this and that is y2 minus y1, and z is between x minus y1, x minus y2. But if x is in the ball of a radius little r, if s is in the ball of radius capital R, y1 is in the ball of radius little r, this is in the ball of radius capital R plus little r, that is in the ball of radius capital R plus little r. Z being between these 2 points, Z is also in the ball. So I have u of x, y1, minus u of x, equal to c of x, y2, minus u of x, plus something. And this something is less than or equal to the maximum of the gradient of u, y1 minus y2. And so this proves that either when I minimize this, if it is negative infinity, then when I minimize that, it will also be negative infinity. But if one of them is not negative infinity, then we have this estimate of what I call something, which is less than y1 minus y2, the maximum of the gradient of h on the ball of radius little r plus capital R. And every Lipschitz function is differentiable almost everywhere. Therefore, UC is differentiable almost everywhere. And in fact, UC is continuous. We also prove that call this star 1. So what I wrote here is under star 1. If u c is differentiable at y, then there exists a unique x bar in the ball, the closed ball, such that UC of y bar is C of x bar y bar minus u of s bar. So I am saying the maximum is unique at the point of differentiability, which means that when we have star 1, the infimum will be uniquely determined. And again, the way we prove this was I wrote that from this definition, I have UC of y plus u of s bar minus c of s bar y is greater than or equal to 0 for every y. Right? By the definition,
so
less.
In the gradient of h is something that you defined last time.
Say it again.
Is h.
It is the h. So at the beginning, when I was starting the lecture, I said my cost function c of sy is h of x minus y.
Okay.
I am given an h, and I define my cost function
So
through it.
cxy is h of x minus y, right?
Yes. So if you want, you can either write this, or you can write that as gradient y c on the ball R cross the ball R. You can also write it that way. Actually, for arbitrary c, this is what is true. And when c of x, y is h of s minus y, then I replace it by the gradient of h. So UC of y is less than this for every x. And so this is what is true. That is telling me that this functional of two variables, when I fix one of the variable x bar, I get a functional which attains its maximum at y bar. And so the derivative with respect to y bar is 0, which means gradient UC of y bar equal to gradient h, gradient with respect to y, c x bar y bar. But this is negative gradient h, of x bar minus y bar. Because gradient of h is invertible, I have that s bar minus y bar equal to gradient h inverse applied to negative gradient of uc of y bar. And so x bar is uniquely determined. By symmetry, so by symmetry, if I write VC of x, this will be the infimum over y in RD, C of x, y minus V of y. And so by symmetry for each x, where VC is differentiable, the minimum y will be unique. So if C was not, if C of xy was not C of yx, here I'll write a U, C, upper C. And here I'll write a V, lower C. But because C is a symmetry, the upper C and the lower C are the same. And I didn't want to make my notation heavier. This is why I assume that H is even. So here, by symmetry, we also prove that so I wanted to say we also prove that there exists a minimizer, but since I said we prove uniqueness, then it includes the sentence of existence. Yes.
Yes.
Yes. So if I want to use the Euclid approximation, I'm going to divide the C by epsilon and let the epsilon go to 0. Yeah. Yes, and the role of the Euclid approximation is you want to prove that every upper semi-continuous function can be approximated by Lipschitz function. And you use exactly this to get Lipschitz. You let epsilon go to 0, and you show that you have a limit. So the next theorem, I am trying to change topic a little bit so that you are less, hoping you will be less bored. So the next theorem was independently discovered by Varadhan and myself. Actually, Varadhan did not write a proof, but he told verbally someone that this is how the proof will. The result is true, and then I heard that later. So let me start with one notation. Summary. Suppose V is from the closed ball to negative infinity plus infinity is upper semi-continuous. Okay. So this may look different from what I was saying. In fact, I am going to take of that V, and I am going to extend it to be negative infinity outside the ball. So defining V on that ball, closed ball, is equivalent to defining V on RD and imposing that it is negative infinity. But since I am going to minimize only on the ball, I will not worry about the V outside the ball. Define VC to be the C concave transform of V bar, where V bar of X of Y equal to V of Y when Y is in the ball, and equal to negative infinity where Y is not in the ball. So in other words, VC of X is the infimum Y in the closed ball of a radius R, C of XY minus V of Y. Suppose V is not identically negative infinity. And so we are back to this situation where the Lipschitz where V is locally Lipschitz. For each X in RD such that the gradient VC of X exists.
You mean VC different from minus infinite or V minus infinite? You mean suppose V is different from minus infinite or VC?
Yes, V.
It's V.
Yes, so I will say suppose V and VC. Suppose V and VC are not minus infinity. Because if V was minus infinity, VC will be identically plus infinity. So let S be such that the gradient of VC at X exists. Define T to be T of X equal to Y, to be the unique Y in the closed ball such that you C VC of X plus V of Y equal to C of X, Y. Okay, so I just wrote before that at the point where we have differentiability, we have a unique minimizer. And I can give a name to that minimizer. Then the mapper T coincides with a Borel mapper except on a set of zero measure. Then T coincides with a Borel map up to a set of zero measure. And in fact, what I am going to do, I am going to find a Borel set of full measure where T is continuous. And if we have that, then we'll be done with the fact that T coincides with a Borel map up to a set of zero measure. So proof. Set S to be the set of X in RD such that the gradient of UC of X, VC of X, exists. I claim that T is continuous on this set. Assume, claim, T is continuous on X. Proof. Assume Sn is a subset of S converges to S infinity. I want to prove that S infinity is a T. So assume that and S infinity belong to S. I want to prove that T of Sn converges to T of S infinity. This is continuity. Okay. So here is the goal. T of Sn converges to T of S infinity. If you want to prove that a sequence converges to a specific point, it is enough to prove that whenever you subtract a subsequence, you can find another subsequence converging to that point. Or another way to say it is assume by contradiction that this doesn't hold. Then it will mean that I can find a subsequence such that T of Snk minus T of S infinity is bigger than a positive number epsilon. I am going to extract a subsequence of T Snk, which is going to converge to T of S infinity, and I will get a contradiction. So assume without loss of generality, extracting from T Sn so why can I can extract a subsequence? Tsn is an element, is a subset of the ball of radius r. Extracting from this a subsequence, if necessary, we may assume that the limit when n goes to infinity, t Sn equal to y exists. By definition, C of Sn, T of Sn, is Vc of Sn plus V of T Sn. By definition, T of Sn is a point where the minimum is attained, and so we have that equality. I let n go to infinity. This function is continuous. That function is Lipschitz, and so it is continuous. This function is upper semi-continuous. Therefore, the lim sup of this will be less than the value at the point. So, since C is continuous, Vc is Lipschitz, and V is upper semi-continuous, we conclude that C of x, y is the limit of C of Sn, Tsn, which is the limit of Vc of Sn plus V of Tsn. This limit existing, the limit of the sum existing, it means that that limit exists. So this is equal to Vc of Sn plus the lim sup over n V Tsn, which is smaller than or equal to Vc of x plus V of y. So this means that y minimizing. If I look at this definition is telling me that this inequality holds everywhere. If the reverse inequality holds somewhere, it means that y is a minimum. Hence, Vc of x, hence y is. So let me rewrite it. Let me rewrite what is there. I have C of x, y minus V of y is less than Vc of x. So I just rewrote, copy what is there. But by definition, this is always greater than or equal to Vc of x. Since Vc is differentiable at x, then y is necessarily t of x. So let me check my notation. It was s infinity. So this is x infinity. that is S infinity. This is S infinity. And so we have continuity. So since we have continuity, I just need to know some good property of this set S. If I know some good property of the set S, then I can conclude that I have a Borel function. Okay. So again, if this continuity, I was able to prove it on the whole RD, then immediately T is a Borel function. But I have proved continuity on this set. But this set may not have some nice property. It may not be a set of full measure. And so I need to check that this set has some nice property. Second property of S. I am going to look at the set of X such that the limit n goes to infinity, Vc of X plus Ei over n minus Vc of X over 1 over n, the lim f equal to the lim sup. So here Ei is 0, 0, 1, 0. I put 0 everywhere except at the I component. Okay. So the partial derivative is the limit. The partial derivative of v with respect to Si is the limit when h goes to 0 of v of x plus h, Ei minus v of s divided by h. So I'm taking h equal to 1 over n. So this limit exists if and only if the lim f equal to the lim sup. That function at the top is continuous because v is Lipschitz. This second function is continuous. So this ratio, I divide by a real number. This ratio is a Borel function. My set is the set of S such that this Borel function equal to that Borel function. Therefore, it is a Borel set. If I impose that all the derivative, the first derivative, the second, the derivative of Vc with respect to S1, with respect to S2, and so on exists, I am taking the intersection of these sets. So call this Si. We have S is a subset of the intersection I from 1 to n, I from 1 to the dimension d of Si. Call this S star. And S star is Borel. This set is Borel. This set is a set of a full measure, which means that this set is a set of full measure because it is a bigger set, which implies that this set is measurable. Okay. So I have a smaller set. I have a bigger set here. And the complement of my bigger set is a Borel set of small measure. The complement of my small set is necessarily of zero measure. This implies that S is measurable with respect to the Lebesgue measure. And so it is a Borel set up to a set of zero measure, because this is the difference between Borel set and Lebesgue measurable set. The Lebesgue measurable set are Borel set up to a set of zero measure. Therefore, I can find a continuous function on this set, S, which is a Borel set up to a set of zero measure. And so my T is a Borel function. Theorem. So this is due to me in 1995, and then independently to Varadhan, and to myself and Maken, 1995. So here, these two were, for the case C of sy equal to x minus y squared over 2. And here is C of xy is h of x minus y. Let V be as in the summary. Okay. So I am assuming that V is lower semi-continuous. And I am assuming that V and V, the C concave transform of V, is not negative infinity. Let phi be a function of compact supple, which is continuous, and define U epsilon of S to be the infimum Y in the ball reduce R, C of x, y, minus V of y, minus epsilon phi of y. So in other words, I am writing that this is V plus epsilon phi, the C concave transform. Then, first of all, U epsilon minus U0 is less than epsilon, the L infinity norm of phi. And second, the limit when epsilon goes to 0 of U epsilon of x minus U0 of x divided by epsilon is negative phi of t of x whenever U0 is differentiable So VC is differentiable at x. And so since we know that this is differentiable almost everywhere at S, it means that this equality holds almost everywhere. So proof. First, fix x in RD. Write U epsilon of x equal to C of x, certain y epsilon minus V of y epsilon minus epsilon phi of y epsilon. So last time we proved that because if a function is upper semi-continuous, the infimum exists. Then I can conclude that, call this one, U epsilon of x is greater than U0 of x is the infimum over y, C of x, y, minus V of y. Therefore, U0 is less than C of x, y, minus V of y for every y. So I can write that this is bigger than U0. This is U0 of x minus epsilon the number L infinity. Call that 2. We have U0 of x equal to C of x, y naught, minus V of y naught for some y naught. So I can subtract something and add what I have subtracted. So now this is bigger than U epsilon of x plus epsilon phi y naught. And so U epsilon of x minus U naught of x is less than or equal to negative epsilon phi of y naught, which is less than the absolute value of epsilon phi to L infinity. Call that 3 by 1 by 2 and 3. We have 2i. We have I. Claim. If U naught is differentiable at x, then the limit when epsilon goes to 0 of y epsilon must be equal to t of x. And the proof will be very similar to what I did before. If you want to prove that y epsilon converges to t of x, it is enough to prove that if you take any sequence, any subsequence of y epsilon, you can extract another subsequence which converges to t of x. So assume the limit when k goes to infinity, y epsilon k equal to y for a sequence epsilon k in 0 in R converging to 0. Then I pass to the limiter here. And I am going to recall that V is upper semi-continuous, which means negative V is lower semi-continuous, which means that the lim f of negative V of y epsilon k is greater than or equal to negative V of y if y epsilon k converges to y. Let epsilon k tend to 0 in 1. Then, by I, U epsilon converges to U naught. Then, using I, the fact that C is continuous, and V, negative V is lower semi-continuous, we have that U0 of x equal to that limit so that will be greater than C of xy minus V of y, and this goes to 0. Hence, y equal to T of x. So whenever, let us recall that this is Vc of x. Okay? When epsilon equal to 0, U naught is Vc. And what is true is always, this inequality is always true. If the reverse equality it holds somewhere, it means that the infimum is attained there. But because S is a point of differentiability, there is a unique point where the minimum is attained. So this concludes the proof. Corollary. Suppose U, V is in UC, maximizes J over UC. And V is as in the previous theorem. Let T be the map. Let T be such that Vc of x plus V of T of x equal to C of x, T of x. Then T is optimal. And so if I finish the proof of that corollary, it means that it suffices to prove that J admits a maximizer, and I'll have found an optimal map. Then T is optimal for a Monge problem. So proof. First, I claim that T pushes mu naught to mu 1. And then I am going to check that among the map which pushes mu naught to mu 1, T has the smallest cost. So this claim amounts to proving, do I have the integral of phi of T of x mu naught dx equal to the integral of phi d mu naught for every phi which is continuous compact support. If I can prove that, then it means that T pushes mu naught forward to mu 1. Because when phi equal to a characteristic function, this is exactly the definition of T pushes mu naught forward to mu 1. And we've seen several times that having this equality for all characteristic functions is equivalent to having it for all functions which are continuous and of compact support. So you can already see the connection with this theorem. Proof. Let phi be continuous of compact support, and define the function f epsilon equal to j of u epsilon v plus epsilon phi. Okay, let me j of u epsilon V epsilon, where U epsilon equal to V plus epsilon phi, and V epsilon equal to V plus epsilon phi. Let me compute the derivative of f at 0. F epsilon minus f0 divided by epsilon equal to the integral of u epsilon minus u naught divided by epsilon d mu naught plus the integral of phi d mu 1 over rd. Now, the previous theorem tells me that u epsilon minus u naught over epsilon is less than phi, the L infinity norm. Therefore, I can apply the Lebesgue-dominated convergence theorem and pass the limit from outside to inside. Since, by the previous theorem, u epsilon minus u naught divided by epsilon is less than phi infinity, we conclude that f epsilon, f prime of 0, is the integral over rd, the limit when epsilon goes to 0, u epsilon minus u naught over epsilon d mu naught, plus the integral over rd of phi d mu 1. But this limit is negative phi of t d mu naught. Okay. The previous theorem tells me that u epsilon of x minus u naught of x over epsilon goes to negative phi of t of x almost everywhere. So this is where you use that mu is absolutely continuous with respect to Lebesgue measure. That equality holds almost everywhere. Because mu naught is absolutely continuous with respect to Lebesgue measure, it holds mu naught almost everywhere. Since phi attains its minimum, its maximum at 0, phi prime of 0 must be 0. So my assumption was uv maximizes j over uc. Since u epsilon, v epsilon belong to uc, it means that f attains its maximum at 0. And so the derivative of f at 0 must be 0. But let me write what it means that the derivative is 0. It means the integral over rd phi composition t d mu naught is the integral over rd of phi d mu 1. Phi being arbitrary, since phi is arbitrary, we have proven that t pushes mu naught forward to mu 1. Next, optimality. Let S from RD to RD be Borel such that S pushes mu naught forward to mu1. I want to show that the cost associated to S is bigger than or equal to the cost associated to T. U of X plus V of S of S is less than C of X, S of X. In fact, if I put XY, I have this inequality. In particular, for Y equal to S of S. But U of X plus V of T of S equal to C S T of S, mu naught almost everywhere. So I integrate the first equation to have that the integral over Rd of U d mu naught plus the integral over Rd of V composition T d mu naught equal to the integral over Rd of C of S, S of S mu naught dx. The second equation tells me the integral over Rd of mu U d mu naught plus the integral over Rd of V composition T d mu naught equal to the integral over Rd. Here is less than or equal to C of S T of X mu naught dx. So why am I done? Exactly. If I use this property, if I use the property that T pushes mu naught forward to mu1, this is independent of S. This is the integral over Rd of V d mu1. This is the integral over Rd of V d mu1. In other words, I have data J of UV equal to the Monge cost of T and is less than or equal to the Monge cost of S. So we have established duality, and we have proven existence of a minimizer. This means that this is the work left. If we can do that, then we are done. uniqueness. Although I didn't claim uniqueness there, let me state uniqueness. If S pushes mu naught forward to mu 1, then at each x such that Vc is differentiable, either S of S is T of x, or U of x plus V of S of S will be strictly less than S of x. Okay. So at point of differentiability, we saw that there is a unique y such that equality holds, and that y is a T of x. So either S is a T of x, or if it is not T of x, we have strict inequality. So call this set B. So call the set A is a set where S is T. Then we have the integral over A of U d mu naught plus the integral over A of U composition S d mu naught plus the integral over B of U d mu naught plus the integral over B of U composition S d mu naught This is the integral over RD This is strictly less than the integral over B of C of S, S of S, d mu naught, plus the integral over A of C of S, S of S, d mu naught, if the measure of B is not 0. So if the measure of B is not 0, on B we have this strict inequality. When we integrate on a set of non-zero measure, we have a strict inequality. But this is the cos, the Monge cos of S. And that is J of UV. But J of UV is the Monge cos at T. And so the Monge cos at T is strictly less than the Monge cos at S. This proves uniqueness. Hence, unless the measure where S is not a T is 0, S does not minimize. The Monge cos. So tomorrow, the task I am going to complete is to prove that we have a maximizer for J over UC, and to prove that the maximizer satisfies the condition that so the condition in the previous theorem, I was assuming that V and VC is not identically negative infinity. So we'll need to prove that. And if we do that, this means we are done for existence of a solution for the Monge problem when the density are absolutely continuous with respect to Lebesgue measure and are of compact support. And the next week, on Monday, I am going to derive the result by approximation. I'm going to derive the result for any probability measure mu0 and mu1. So for any probability measure mu0 and mu1, it is not true that there exists an optimal map from Monge problem, but the fundamental result we are after is the duality result. Okay, I say I'm going to stop here.
Do you want to tell them about the web page?
Oh, yes. So,
next time?
so